Can you hear me well on Zoom? On Zoom also? Is it good? Okay. Okay, let's get started in half a minute. Okay, I guess it's time. So welcome to lecture 11. We're going to continue microarchitecture fundamentals and design. And specifically today, we're going to focus on multi-cycle microarchitectures. Remember, last lecture, we focused on designing a microarchitecture from the ground up. We designed a single-cycle microarchitecture from the ground up, both the data path as well as the control logic that's required to execute the instructions. Today, we're going to figure out the problems with it. We kind of talked about them last time also, but we're going to talk more and then design something better. Does that sound good? Cool. Okay. Can people hear me in the back? Is it okay? Do we need to raise the volume at all? I guess not. Okay, that's good. Okay. So just to remind you, the state deadline is coming up. If you want to get some extra credit, April 1st, which is in 2 days, I think. And then there's another extra credit assignment that you know of. Okay. So this is the plan for today. Today, I intend to finish MultiCycle Microarchitecture. And if we're really fast for some reason, which I don't anticipate, we can start pipelining a little bit. But tomorrow, we'll start pipelining. And then next week, we're going to talk about issues in pipelining. And then we're going to do that for probably one lecture. And then we'll go into out-of-order execution after the Easter break. Does that sound good also? Okay, good. So you'll have some break to think about how can you do better than pipelining, let's say. So readings, this is basically the same as what I put earlier, except this is going to be also this week, the pipelining part. Okay, so we were talking about implementing the ISA, the Microarchitecture Basics, and some of the slides I'm going to go over that you have seen before. Basically, we designed a very basic instruction processing engine where each instruction takes one single clock cycle to execute. So there are no intermediate programmer invisible state updates, meaning there's no microarchitectural state updates. And this is what the machine looked like, basically. It transforms, a given instruction transforms architectural state before it to another architectural state in one clock cycle, one machine clock cycle, based on the ISA specification of the instruction. Okay, and basically all of these steps in an instruction are done in a single clock cycle, and all of the instructions should be able to finish in the same clock cycle. And this is one of the downsides, as we will see, as we have seen also. But basically, this is also what you have seen. In a single cycle machine, all 6 phases of the instruction processing cycle takes a single machine clock cycle. That's not true in multi-cycle machines that we're going to build today. We can take multiple machine clock cycles. In fact, each phase can take multiple machine clock cycles to compute. But this is a single cycle machine. Basically, it looks very simple. It looks like this. You have sequential logic, which is the architectural state, and then combinational logic produces architectural state prime based on the specification of the instruction. And you have to provide the combinational logic to execute every single instruction specified by the instruction set architecture. Makes sense, hopefully, right? Okay. And you also learned the concept of data path and control logic. Basically, data path consists of the hardware elements that deal with and transforms the data signals. It contains functional units that operate on the data, ALUs, for example, hardware structures that actually enable the flow of the data between functional units and registers and memory structures, storage units in general, like wires, muxes, decoders, etc., and storage units that store the data, registers and memory. And then control logic is separate. I mean, in fact, we designed these separately, right? We first designed the data path to execute simple instructions, and then we kept adding to the data path so that we can execute more instructions. And we said there are control signals, but we didn't design the control logic. And then we designed the control logic as a function of the instruction that's being executed and some things that are needed from the data path, like in case of a taken branch instruction or, in case of a taken branch instruction, or conditional branch instruction more generally. So control logic consists of the hardware elements that specify or that determine control signals. In other words, signals that specify what the data path elements should do to the data. How should the data flow? Where should the data flow? How should the registers get updated, for example? And we did this, so I'm not going to go through this. Basically, we designed a SingleCycle microarchitecture from the ground up. We designed the SingleCycle control logic. If you don't remember, please watch the prior lecture again, maybe. But basically, this is the SingleCycle microarchitecture we developed in the lectures. It's beautiful. And your book also has a very similar SingleCycle microarchitecture. We actually briefly went over pieces of this. We're going to go over this a little bit more today. So this is the SingleCycle processor in your readings. How many people have done the reading for SingleCycle? Don't be afraid. Okay, that's good. There are people who are doing the readings. As I said, if you understand everything perfectly, you don't have to do the readings. So now we're going to evaluate the SingleCycle microarchitecture. We kind of did this, but we're going to do this a bit more methodically today. I don't think they need to listen to our lecture, do they? Okay. There's an ordering of doors here. Okay, so we're going to do it a little bit more methodically. I think we've already kind of answered this, right? Is this a good idea design? So how do you evaluate something methodically? Basically asking the question, is this a good idea? Is this a good design? Is it a good point to start? How many people say this is a good idea, SingleCycle? How many people say this is a bad idea? Okay, that's good. So we're going to go through this quickly then. But I think maybe it's better to ask the question in a more finer manner. When could this be a good idea? Could this ever be a good idea? That's always a good question to ask. And maybe the answer at that point is potentially, right? Depends on the latencies of different instructions, I would say. In practical cases, this is usually not a good design though. When is this a bad design? We will see this, and we already talked about this, but basically the latency is determined by the worst case processing latency of any given instruction. And some instructions fundamentally take much longer in terms of combinational logic. And your critical path is determined by those instructions, whereas some other instructions can take much shorter. Now your clock cycle is determined by the longest taking instruction, right? So it's usually a bad design when there's a huge disparity between the instructions and instructions take long, right? And which is usually the case in real life. If all of your instructions actually required very short latency, and also they were uniform in terms of the latencies more or less, maybe this could be a good design, but in practice that doesn't happen much. So basically, how can we design a better microarchitecture will be our question to ask every time we introduce a new microarchitecture. We will say, can we do better? Can we do better? We're going to introduce, for example, MultiCycle microarchitectures. I'm going to end with, can we do better than this? Next lecture, we're going to start with pipelining. We're going to finish pipelining, and we're going to say, can we do better than this? We're going to talk about out-of-order execution, and we're going to ask, can we do better than this, basically? That's how things improve. If you don't ask this question, if you don't do this critical thinking, things don't improve. And there's no point of having universities then, right? Okay, so let's talk about performance analysis basics. We also discussed this, but in order to really make principled decisions and answer these questions well, it's good to have a principled framework where you can evaluate some metrics. And I've already shown you this slide. Basically, we just define the execution time of a single instruction, and we're going to focus only on performance at this point, not energy. Energy is a different ball game, but it has some correlation between performance with performance as well. But focus on performance, which is execution time. And execution time of a single instruction is how many cycles does it take to execute that instruction, CPI, cycles per instruction, times the clock cycle time that you determined based on the critical path of your sequential design. That simple finite state machine that we saw. But yeah, I already just defined this. And the execution time of the entire program is the sum over all of the instructions that is executed by the program, this value, which is cycles it takes to execute the instructions times the clock cycle time. And we said that you could actually write this as an average cycles per instruction. You average the cycles per instruction across all of the instructions, and you can decompose this equation into three distinct pieces. One is the number of instructions you have in the program. The second is how many average cycles do you take to execute that mix of instructions that you're executing, and what is the clock cycle time. And we said that you could actually optimize these things differently, right? Okay, so let's go over this a little bit more, basically. I think we already said this. Every program consists of a series of instructions, and each instruction needs to be executed, right? And instructions are realized on the hardware. Each instruction can take one or more clock cycles to compute. That's what cycles per instruction is. So how long is one clock cycle? We already discussed this also. Remember the timing and verification lecture especially. The critical path is determined by how much time one clock cycle requires. This is also called the clock period, if you remember. And clock frequency is essentially the inverse of it, 1 over the clock period, right? Hertz is, for example, 1 over second. That's a metric for frequency, right? And it basically means that how many clock cycles are in 1 second. So basically, as a general formula, you have a program that consists of executing n instructions. This is n dynamic instructions. How many instructions are actually executed in the machine to finish the program? And the processor needs CPI cycles on average for each of the instruction. And the clock frequency of the processor is f, meaning that the clock period is 1 over f. So essentially, this is how you arrive at the equation that I showed you earlier. Your program executes in n times CPI times 1 divided by f seconds, or n times CPI times the clock period seconds. This makes sense, hopefully. Okay, so now let's analyze a single cycle design based on this. We'll get back to this equation later on. So you can really improve system performance by improving all of these metrics at the same time, potentially. But sometimes there's tension between these metrics. For example, when you try to reduce cycles per instruction, clock period may increase, or vice versa. When you actually increase the cycle per instruction, you can actually reduce the clock period. And we are actually talking about that trade-off right now. Okay, so let's take a look at the single cycle design. Basically, in a single cycle design, by definition, every instruction takes 1 cycle, 1 clock cycle to execute, and CPI is strictly 1, right? But how long each instruction takes to execute is determined by the slowest instruction to execute. Even though many instructions may not need that long to execute, right? For example, an add may need only some combination logic, but a more complicated load instruction may need much more combination logic to execute, much more delay in the combination logic. So basically, as we discussed last time also, a clock cycle time of the single cycle microarchitecture is determined by how long it takes to complete the slowest instruction. Now, of course, this brings out about the question, what is the slowest instruction, right? How bad is this? This is where you run into trade-offs. This is where you need this nuance in the question that I asked, right? Is this a good idea? Well, it depends on the slowest instruction, basically. Basically, in general, when we ask questions in design, the best answer is it depends. Of course, it's an escape answer, right? Is this a good idea? Well, it depends. Tell me more. What should I tell you more? Well, what is the slowest instruction? How long does it take? If that's fast enough, maybe that's a good idea, right? So that's basically the importance of trade-offs in the end. So if you're wise, it's always good to answer the question, it depends, and tell me more. But of course, you need to be able to ask the next question then. What should I tell you more? Okay, so here you know what to tell, what to discover or what to know more, which is the slowest instruction. Basically, the critical path of the design is determined by the processing time of the slowest instruction. So what is that? So we need to, for that, to figure that out, we need to go back to the basics, which is what is the instruction processing cycle? Basically, all instructions go through this processing cycle. Some of them do not need the stages, but some of them need all of the stages. And probably those instructions that need all of these stages take the longest, assuming that there's a very strong correlation between the paths that are executed on the critical path and the stages, right? And there is actually. So we remember we actually designed our processor this way using 5 stages actually. Processing stages. So the question is basically, does every instruction take the same time or latency to complete? Well, let's take a look. Let's find the critical path in our design. So this is the design that we made from the ground up last time. Now we're going to have some more fun with it. We're going to basically assign some values. So basically, this is what we're going to assume in the design. For the design that we actually created last week, let's find the critical path for different instructions. So we're going to assume these things. Memory units, either read or write, take 200 picoseconds. Kind of magic, but sure. ALU and adders, each of them take 100 picoseconds. Register file, read or write, takes 50 picoseconds. And we're going to assume everything else is ideal, meaning they have no delay, which is of course not true, but that makes our life easier in analyzing what we're going to analyze, right? So basically, this is any logic or wire delay or sequential latching delay. We're going to assume all of that is 0. Clock skew, it doesn't exist, right? In reality, you need to deal with that to find the critical path. And basically, we're going to look at 6 different types of instructions: R type, I type, load word, store word, branch, and jump. Branch, conditional branch. And we're going to look at basically these 5 different stages or steps, and we're going to look at the different resources each steps exercise. And I already kind of did that for you over here. You could do the spreadsheet type of analysis actually, based on what I just wrote over here, by looking at which instructions actually go through which steps or stages. And you can see that the memory instruction, load word instruction, actually exercises all of these steps, 5 steps. And as a result, it incurs the delay in all of those, and it's the longest instruction. So its delay is 600. Whereas the fastest instruction in the combinational logic path is only 200, as you can see, which goes through fetching the instruction. And everything else we assume that doesn't take. Because if you remember jump, what it does is you fetch the instruction, you concatenate the program counter with the bottom n bits. We are assuming that that takes 0 cycles, right? Okay. Okay, so let's look at it. Let's look at each of these in the pipeline. Well, not pipeline, sorry, in the microarchitecture that we designed. So this is, let's say, this is what we're going to do. We're going to find the critical path of R-type and I-type ALU instructions. So what do these instructions do? They basically get fetched. So you need to take the program counter and fetch the instruction, meaning that you incur this memory latency, which is 200 picoseconds. And then they go through this mux, which is magic, 0 latency. You access the register file, which I told you was 50 picoseconds. And then ALU instructions do some ALU operation. So you go through the ALU, which I told you was 100 picoseconds. And then they don't have anything to do with memory. They write back to the register file, which takes another 50 picoseconds. Right? So if you add those up, which I did over here, you would get 400 picoseconds on this path. So this is one potential path that could be critical in the execution of R-type and I-type ALU instructions. And R-type and I-type, the difference is basically these muxes, if you remember, right? When we built the pipeline, well, also the sign extension logic, but we're kind of assuming that those are magic 0 picoseconds, right? So that's why these are the same in terms of critical path. In reality, they're a bit different, of course. Does that make sense? So this path is 350 picoseconds, but that's not the only part of the instruction. The instruction also specifies that you should increment the program counter. So there's another path that you exercise in the data path, which is this adder. You increment program counter by 4 for all of these R-type and I-type instructions so that you can get to the next sequential instruction. And that's the critical path over here. And that goes through some other muxes, multiplexers, if you remember. These are there for jumps and conditional branches. But we're assuming those multiplexer delays are 0. That's why it's just 100 picoseconds. If you assume some delay for them, this will be 100 picoseconds plus multiple multiplexers delays, which is not going to be as long as memory access plus register file plus ALU plus another register file, right? Plus other muxes that are exercised over here. So basically the critical path for R-type and I-type ALU is, you can see that 400 picoseconds, right? Does that make sense? We did this critical path analysis and timing and verification in a more rigorous way. We looked at every single gate. Right now, we're actually raising the abstraction level a bit, and we're using the values that I just gave you in this slide, right? Okay, so now you know how to do the critical path analysis, assuming that you're given these numbers, which could be a not so bad exam question, right? Okay, load word, let's take a look at it. Basically, you do the same thing. Load word also needs to increment the PC, so don't ever forget that path. It's not the critical path, but it could be, depending on what you really need to do. In load word, you can see that you need to fetch the instruction. You need to fetch the registers. You need to go through the ALU to add the register to an offset coming from the instruction. And then you need to access memory. And then you need to write the data back to the register file. So basically, you incur 200 picoseconds in memory, 50 nanoseconds in the register file access, 100, not nanosecond, picoseconds, 100 picoseconds in the ALU, 200 more picoseconds to access memory to get the data, and 50 more picoseconds to write the data to the register file. So that's 600 picoseconds. And this turns out to be the longest delay, assuming these numbers. Okay, store word, very similar to load word, except you don't write back to the register file, right? You compute the address similar to load word, and then you write the data into memory, which we assumed is 200 picoseconds. So it's only 50 picoseconds short compared to the load word. And again, we're ignoring this because it's too short. So let's take a look at branch taken. Can the branch taken be longer? Potentially, depending on what you do in the branch taken. Remember, in MIPS, branch equal, for example, you fetch the instruction, you get 2 registers out of the register file, and then you compare them through the ALU, that's another 100 picoseconds. And then if the branch is taken, this multiplexer will select this output of this adder. So the critical path can potentially be the select input of this multiplexer or the data input of this multiplexer. So you need to actually compute the data, how fast the data input arrives into the multiplexer. So select input, based on what I told you, arrives after 350 picoseconds to this multiplexer. The data input arrives after incrementing the program counter and then adding a sign extended left shifted offset to it to compute the target address as specified by the conditional branch instruction. And that takes 200 picoseconds. That takes 100 picoseconds because we assume that the adder is 100 picoseconds and this other adder is also 100 picoseconds, and shifting left doesn't take time. So basically, this data input into this multiplexer arrives after 200 picoseconds. So this is really the critical path, 350 picoseconds. Okay. So basically, a branch taken under the assumptions that we have discussed and under this data path design and the control logic design. Well, let's get back to control logic a little bit later. Under this data path design, it takes 350 picoseconds. Let's take a look at jump. Jump is actually the fastest, as we will see, because jump, you fetch the instruction, and then the instruction goes through some control logic, and you select the appropriate multiplexer data input. And what should the data input be? Unconditionally, because it's an unconditional jump, the data input should be PC incremented by 4, concatenated with 26 bits coming out of the instruction, left shifted twice, 2 bits, of course. And that's, so this is a potential critical path, the multiplexer data input, which is the target address. And the other potential critical path is the select input, which comes after the instruction fetch. So basically, instruction fetch is happening concurrently with incrementation of the PC, as you can see. And incrementation of the PC is 100 picoseconds, instruction fetch is 200 picoseconds. So the critical path is really 200 picoseconds because we're ignoring all of the other logic and multiplexer delays, right? So you can see now that jump is the fastest instruction to execute. It doesn't exercise anything over here. Make sense? So basically, we've gone through all 6 categories of instructions for which we designed the data path. And now we've seen that the slowest instruction is 600 picoseconds. The fastest instruction is 200. And maybe very common instructions are 400. So it's a distribution, as you can see, right? So basically, what should you set the clock cycle time to? Basically, the slowest instruction. Your clock cycle time cannot be lower than 600 picoseconds plus other overheads, sequential logic overhead, which we kind of ignored in this particular single cycle design. Even though whenever you execute a jump, you're wasting 400 picoseconds of that clock cycle. Or when you're executing an R-type add, for example, or I-type add, you're wasting 1/3 of that clock cycle. So that's the downside, basically. There's a lot of waste in the clock cycle here because the slowest instruction takes very long. Any questions? Okay, here we've kind of ignored the control logic because of our assumptions, right? Any other logic takes 0 cycles, but potentially control logic can affect the critical path also. It depends on how fast you can generate the control signals, because in a single cycle design, you have to generate the control signals before the data path can process them, right? So control logic can actually get into the critical path significantly. And that's one of the reasons why single cycle design is not that great. In the multi-cycle design, you're going to see that you can overlap the processing in the data path with the generation of control signals in the next cycle that are needed in the next cycle. Here, it could get in the way. And actually, there were machines in the past where control logic could be were on the critical path. But people quickly figured out that you can design around this. So for example, in the old machines, CDC 600, CDC, this is the Control Data Corporation. This was a very small company that was competing with IBM in 1960s. And they actually designed the first out-of-order execution processor before this huge IBM company did. So they were actually quite good in designing, but in their initial machines, control accesses actually took so long. Okay, now that's what we looked at, right? 600 picoseconds doesn't sound too bad, right? But what is the reality today? So basically, we've kind of assumed that memory is magic here, right? 200 picoseconds. If you want to actually design a real memory, large memory, it doesn't take 200 picoseconds today, basically. So this is the real killer for a single cycle microarchitecture, actually. What if sometimes memory takes 10 milliseconds to access? Potentially it could. If you have terabytes and terabytes of memory, you may need to take milliseconds to access, right? Are you going to set your clock cycle to 10 milliseconds? Probably not. Oh, okay, maybe even if you say 150 nanoseconds, which is more realistic for main memory. But if you actually don't have the data in main memory, where do you go? You go to disk, for example, right? Okay, let's assume that everything is in the main memory. Then do you set your clock cycle to 150 nanoseconds plus all else to perform a memory operation? Okay, let's say 200 nanoseconds. That's very slow, right? Today, clock cycles are on the order of, I don't know, 6 gigahertz, let's say. 150 nanoseconds will not get you anywhere close to 6 gigahertz. 1 nanosecond is 1 gigahertz, basically. 150 nanoseconds is 150 times slower. So basically, it does not make sense to have a simple instruction to take as long as a much more, let's say, I don't want to call it complicated, but longer latency instruction. And that's the problem with the single cycle microarchitecture. It requires every single instruction to take as long as the worst possible instruction takes. And then, of course, the problem is even worse, right? What if you need to access memory more than once to process an instruction? Actually, every instruction requires one memory access, right? You need to fetch the instruction, right? This is actually a good question also. Which instructions require memory access? Every instructions require memory access because you have to fetch the instruction first, right? But some instructions require multiple memory accesses, like load. You have to fetch the instruction and fetch the data. And we've seen an example of an indirect load earlier last week, load indirect in LC3, that requires fetching the instruction, going to the memory once to fetch the address, and then using that, using the data in the location that you actually index into the memory with as another address into the memory. So accessing memory twice. You first access memory to get the address, and then you get you access the memory again with that address to get the data. And then you could keep adding to it, actually, right? You could design more complicated instructions that do multi-dimensional array accesses. You can have actually 10, maybe 20 memory access in a single instruction. Now multiply that 150 nanoseconds with 20. So basically, it becomes unreasonable to process, especially memory instructions. And memory instructions usually take the longest in your design. And we've seen this with load word, right? But actually, the real life is much worse than what we have seen. So basically, single cycle microarchitecture, even though it was good for us to look at, it's basically unreasonable. Well, this slide base says it's unreasonable in general. It has a lot of complexity because in the end, it's contrived. Why? Because all instructions run as slow as the slowest instruction. This breaks some rule, principle that we introduced actually last time. We're going to talk about that. Inefficient, because all instructions run as slow as the slowest instruction. There's a lot of wastage. And also, there's a lot of wastage in terms of time, right? So longest instruction takes 600 picoseconds. Some instructions take 400. So some of your clock cycle is wasted. But also, you need to provide worst case combinational resource in parallel as required by any instruction. I don't know what happened here. By. That should be by. So the reason is you're doing everything in one clock cycle. And you cannot reuse hardware because of this. So you may, for example, if an instruction needs to do 5 additions, and some instructions actually need to do that, you need to have 5 adders to do it. You cannot reuse one adder to do multiple different additions because otherwise you'll clobber the signals, right? So this increases the hardware cost of single cycle architectures. We're going to see this also. And this means that you need to replicate a hardware resource if it's needed more than once by any instruction during different parts of the instruction processing cycle. So for example, a load instruction needs to calculate an address once. If you need to calculate the address again and again and again to access multi-dimensional arrays, you need to go through multiple different adders for that purpose. And this is not necessarily the simplest way to implement an ISA because this is especially tough for complicated instructions. Remember, we were talking about complicated versus simple instructions. If you have a string copy, x86, for example, has this beautiful instruction. It's called repeat move s, move string. It's a copy, string copy operation, basically. It's actually, the length of this is, I don't want to say unbounded, but the amount of time it takes could be very large. You could be copying 1 million elements, 1 million different characters from one place to another in memory. The question is, does it really make sense to actually do this in one cycle? Well, it doesn't in the end. VAX architecture had this multi-dimensional array access instruction. They called it index. And again, multiple memory accesses. Does it really make sense to do this in one cycle? It's much more reasonable to break these operations into smaller chunks and do smaller chunks in one clock cycle and have more clock cycles to complete. And finally, it's not easy to optimize and improve performance in this sort of architecture, microarchitecture, because optimizing the common case doesn't work. So you have a program, you profile your program, 99% of the program is add instructions. That sounds great, right? You say, I'm going to optimize my adder such that it's fast. It doesn't matter. Why? Because add is not the fastest, the slowest instruction. You have to always optimize the slowest instruction to process. It doesn't matter whether that slowest instruction is going to be executed 0.0000001% or never. You have to make sure it gets executed, and it's a single cycle microarchitecture, so you cannot optimize the frequent case, common case. And remember the common case or bread or butter design that we discussed. Okay, so I think I've distracted single cycle architecture. So you need to optimize the worst case all the time. Does this make sense? Okay, I see a lot of nods, that's good. Okay, so let's go back to these design principles that I introduced. Basically, a single cycle microarchitecture breaks all of these principles. Critical path design, we said that we would like to find and decrease the maximum combinational logic delay so that we can actually have a high frequency design, right? If you want to optimize for performance, frequency is an important component. Remember the performance equation. So for that, you need to break a path into multiple cycles if it takes too long. Single cycle design by definition says this is not possible, right? We don't want to do this. So basically, it breaks the critical path design principle. It breaks the bread and butter or common case design principle. If you recall, this says, spend time and resource on where it matters most. In other words, improve what the machine is really designed to do, improve the common case as much as possible without making the uncommon case, let's say, dictate your performance. I just gave you an example that violates this and does exactly the opposite, right? If your program has 99.9999% adds, it doesn't matter. You cannot optimize for that common case because the uncommon case, which is the instruction that takes longest to execute, dictates your performance. So it completely goes against the bread and butter design principle. And also it does go against the balanced design principle. You cannot balance the instruction data flow through hardware components and eliminate bottlenecks. I'll leave that to you to think about. So basically, I've given you 2 out of 3. You can think of it. And we're going to get back to this actually in multi-cycle microarchitectures that we designed. So this is basically the framework that we introduced last time, right? You have these design principles, you have this performance analysis metrics, and we basically put our single cycle microarchitecture and evaluate it against this framework. It breaks the design principles, and it breaks the performance analysis because we will see that in a little bit. Well, I've already said to you actually, right? You have only 1 degree of freedom to optimize in the performance analysis, which is the clock cycle time. And you cannot optimize it very well because it's determined by the worst case. Okay, any questions? Feel free to ask. Okay, now I can take a little bit of a side over here before I go into the performance analysis of this a little bit more, and then we design the multi-cycle microarchitecture. But basically, I think one of the main reasons why I don't eliminate single cycle microarchitectures in my lectures, even though it's quite unreasonable, as you can see, is to harp the point that we do need to follow these design principles in our designs. So you can actually easily break these design principles. And if you're able to figure out when they're broken, you can actually relatively easily improve designs. So this is an obvious case where all of the design principles are broken, but it's good to know this. So this is actually true for any system design. As I said, this course, even though it's focused on digital design and computer architecture, a lot of these are applicable to real systems, real architectures, buildings, bridges, train stations, and you can imagine that. Good consumer products, and security and safety critical systems, decision-making systems, you can keep adding to it. But remember the principle design from our lecture? Was this the first or second lecture? Probably first. We'll need to correct this. But remember this quote from Frank Lloyd Wright, architecture should be based upon principle and not upon precedent. That's what I'm exactly mentioning. You can evaluate this architecture based on some of your principles. It may violate some of your principles, right? It may not be good for some of the metrics, whereas this could satisfy some of your principles, right? And this was the falling water, if you remember. So basically, that was the purpose of this discussion, the principle design discussion. Now you've seen one example from real computer architecture. Okay, I don't want to harp on this more. But there's another slide that we have seen. Essentially, underlying technology might change in some way. You may be constructing, for example, this processor. Okay, I don't know, let's say CMOS logic that we've talked about, right? Before CMOS, there was no CMOS, there was something else, right? NMOS logic, ECL logic, some sort of different logic. Maybe in the future, it could be something else different, some quantum principles, which we will have to see. But that underlying technology might change, but these principles are actually, I believe, are going to be quite fundamental. And they're going to bear resemblance. Methods of taking advantage of the different technologies will bear resemblance. Okay, so here I will actually point you to some other system design principles before we move on. We will continue to cover them. And here are some references. These are actually some beautiful papers. The first one is written by my PhD advisor. It's beautiful. You can see that. I actually mentioned that in the last lecture. Mike Flynn, who's done a lot of work on computer arithmetic, talks about, how come you're not seeing this? Okay, because I moved. Gene Amdahl's paper, you're reading it, right? Gene Amdahl actually developed a very, so Gene Amdahl's paper actually is about the bread and butter design principle, right? Common case. He basically says in the paper, which you're going to review, maybe I'll give it to you, basically, he says that I'm very pessimistic. He doesn't say this directly, I'm paraphrasing, of course. I'm very pessimistic about using multiprocessors to improve performance because there's a sequential bottleneck, right? The sequential bottleneck, if it's taking 50% of the execution time, the maximum performance improvement you're going to get by parallelizing the program is 2x. So that's a bottleneck for you, right? That's bread and butter common case. So figure out something bigger and optimize your system. Okay, Butler-Lampson also has this beautiful hints for computer system design. So I like some of the other principles. Keep it simple is a good principle. And that's what the beauty of multi-cycle microarchitectures will show themselves in their simplicity soon. Does anyone know who said this? Everything, yes. Yes, very good. Although he never said this exactly, I think it's paraphrased. So this is the paraphrase of Einstein, but it gets the point across by saying it this way, I would say. So basically, everything should be made as simple as possible, no simpler than necessary, because there's some simplicity that level that you cannot go beyond unless you develop a further understanding of that thing. And then there's another principle, which is keeping it low cost as much as possible. And there's this quote. Does anybody know who said this? It's a bit harder, probably. This is anonymous. We don't know. But basically, an engineer is a person who can do for a dime, 10 cents. Sorry for the US-centric terminology. What any fool can do for $1. Okay, for more, see this beautiful paper on hints for computer system design. Butler-Lampson was an early pioneer in the development of computing systems. So he won the Turing Award for the Xerox Xerox Alto system, etc. So he has a lot of principles that he can tell you about. Okay, now we've covered that. Let's talk about can we do better. Basically, we've covered single-cycle microarchitectures. As I said, my question to you would be, can we do better? And I think we already know the answer to this. So that brings us to multi-cycle microarchitectures, which is going to fare much better with some of these principles, but it's not going to be perfect. So what are these? Essentially, our goal is to let each instruction to take as much as possible, only as much time it really needs. Basically, don't waste work. This is a good principle, right? Don't waste time in a clock cycle, and don't waste time unnecessarily, essentially. And you can achieve this by doing this as much as possible, right? So the idea is to break this paradigm of single cycle processing, as opposed to saying everything should take only one clock cycle. Determine the clock cycle time completely independently of instruction processing time, because single cycle microarchitecture has this dependence, right? Because everything takes single cycle, the clock cycle time has to be determined by the worst case combination logic delay of the worst possible or longest taking instruction. But there's another design paradigm that can say, I don't care. I'm going to set my frequency target to 10 gigahertz, and I'm going to do whatever it takes to achieve that 10 gigahertz. You cannot do that with a single cycle microarchitecture, but you can do that with a multi-cycle microarchitecture. Set your clock cycle time, that's your goal, and then design your microarchitecture to achieve that clock cycle time. This is essentially critical path design that we have discussed earlier. So basically, each instruction takes as many clock cycles as it needs to take. Of course, you can optimize that also, right? You can, by doing the data path design and control design carefully, you can try to reduce the cycles per instruction as well. So basically, we're going to have multiple state transitions per instruction. And the states followed by each instruction is going to be different. You kind of remember what this is now, right? So this was the microarchitecture that I threw at you without designing earlier. And that's going to be our design. And this is, remember, again, this was another slide that we covered last time. I'm going to focus on this part especially. basically, we can have there are many choices in implementation of how architectural state gets transformed to architectural state prime given an instruction. The first choice was single cycle, but the second choice, you could have programmer invisible states to optimize the speed of instruction execution. So you can have multiple state transitions per instruction, as you can see over here. So we're going to do that. So another way, this is basically showing the same thing. You have an architectural programmer visible state at the beginning of an instruction. When you fetch the instruction, you have this. And then you process part of the instruction in one clock cycle. That produces some microarchitectural state. You don't change the architectural state in between. And then you process part of the instruction in the next clock cycle. And then you process the instruction in the next clock cycle. You basically take as many clock cycles as you need to finish the instructions processing and then produce the architectural state prime at the end, which is the programmer visible state at the end of that final clock cycle, if you will. This makes sense, right? This was the finite state machine that we looked at in LC3, which is this, if you remember. This was the design that you actually got introduced to the first microarchitecture because it's beautiful. It's much more reasonable than single cycle. As you can see over here, remember what we did in that machine was in state one, we put program counter into the memory address register and we incremented the program counter. And then we went to the next state unconditionally. In the next state, we queried memory with some, and then memory responded with data in the memory data register. And then we unconditionally went to the next state. In the next state, we took the data from in the memory data register and put it in the instruction register. Basically, we fetched the instruction through 3 states. And this is a finite state machine. Each state takes 1 clock cycle. Basically, it takes 3 clock cycles just to do the fetch. We have not even finished the instruction yet, right? And then we decoded the instruction in 1 cycle. And then basically there's a multi-way branch in the finite state machine, as you can see over here. Depends on which instruction it is. Let's assume that it's jump. We kind of assume this here in this slide. And then the jump takes 2 more cycles in this particular case. Well, it could be more actually, but in this case, 2 more. So basically, and then you go back to state 1 to fetch the next instruction. So basically now, if you can see that it takes 1, 2, 3, 4, 5, 6 cycles to finish the processing of a jump instruction. And this says nothing about your clock cycle time. Your clock cycle time is determined by how long it takes to actually finish the worst possible combinational logic delay as dictated by your finite state machine as well as your data path design. So it really depends on how you design, how you implement this finite state machine and real hardware in the data path. It's not dictated by your instruction, if you will, worst case instruction. Okay, and you remember the full state machine. Actually, we'll probably get back to this depending on how fast we progress today. We'll probably get back to this particular finite state machine. We can do actually a lot of cool things with this. Okay, so let's take a look at the benefits of multi-cycle design before we actually design it. So again, we have our framework. These are our principles. And let's take a look at how a multi-cycle design fares in terms of these principles. Critical path design. Basically, you could keep reducing the critical path independently of the worst case processing time of an instruction, of any instruction. That sounds great, right? Now essentially the sky is the limit, or your imagination, your creativity, your ability to design things, and of course, the limitations of the technology are the limit, not the specification of an instruction. Okay? Bread and butter or common case design? Well, if add instructions are 99.999999% of your program, go figure out in this finite state machine where that add instruction is. Okay, let's put that 1, 2, 3, 4. I guess this is the add over here, as you can see, and try to optimize it as much as possible. Right? If load is your bottleneck, let's say, then go figure out in the finite state machine where that load instruction is. Try to optimize it as much as possible. So how do you optimize it? Well, you can optimize the number of states it takes to execute those instructions that really bottleneck you, that make up much of the instruction execution time. You have that freedom right now. You didn't have that freedom before, as we discussed. And balanced design. Balanced design, we didn't discuss the single cycle microarchitecture, but now you can see how it also violates the balanced design principle. Basically, with a multi-cycle microarchitecture, you don't need to provide more capability or resources than you really need. Because you can do things across multiple cycles. If an instruction requires 4 different additions, you can do those across 4 different cycles. Now, what does this mean? This means that you can use a single adder to do all of those 4 different additions, because you're not doing all of those 4 different additions at the same time. You do one addition in one cycle, change the control signals, do the next addition in another cycle, change the control signals, next addition another cycle, change the control signals, next addition another cycle. That's the beauty of this microarchitecture, basically. You don't need to provide more resources than you really need. That's why this is actually a more frugal microarchitecture in terms of design. That's why it's a bit more balanced and easier to deal with. So this is a more formal way of saying what I just said. An instruction that needs resource X multiple times does not require multiple X's to be implemented. X could be anything. Register file access, it could be memory, it could be ALU. Yeah, and we will see that. And also this leads to more efficient hardware in the end, because you can reuse hardware components needed multiple times for an instruction. And we will see this with real examples. Of course, not everything is always upsides, right? As I said many times in this course, it's all about trade-offs. Life's about trade-offs, and clearly design is about trade-offs. What are the trade-offs? Anybody tell me? There's actually one major issue with this design. If you need to do things in multiple clock cycles, what do you need to add to the design? I'm waiting. Don't make me wait too long. Anybody? You need to store these intermediate values somewhere, right? What do you need to add to the design to actually store the intermediate values? Who's going to blurt it out? Additional microarchitectural state. What does that consist of? Yes, please. Exactly. You have to add registers, yes. And registers come with 2 problems, at least. Actually, I could add more problems, but one problem is additional hardware, right? But the other problem is, what is it? You've seen this in timing and verification lectures, right? Time. Meaning you have to put stuff into the registers, and that requires additional time, right? So basically, because we need to store the intermediate results at the end of each clock cycle, there's hardware overhead for these registers that are added, microarchitectural registers, and the register setup and hold overhead that we have seen in the timing and verification lectures. And you pay this multiple times per an instruction, right? This is also called sequencing overhead, if you remember. So in a sense, you're reducing waste, but you're adding a little bit more waste to reduce waste significantly. So this is not a bad trade-off in the end, but you should always be cognizant that you're adding some overhead also. It doesn't come for free. What we're doing is doesn't come for free. There's nothing that comes for free, basically. You may have a great idea, but there's always some other trade-off that you're making. Now, the good news over here is this: I would take this trade-off anytime, I would say, compared to a single cycle design. Because single cycle design wastes much more, if you will. But don't ever think that your idea will come for free. Okay, so let's take a look at it. So this is the multi-cycle LC3 data path that we have seen, if you remember. I'm not going to go through it in a lot of detail, but I'm going to point out these extra registers that are not needed in a single cycle design. So these 3 registers are actually not needed in a single cycle design. There could be more, as we will see later on in some other microarchitecture that we will develop. Okay. Okay, so let's take a look at performance analysis. I actually showed the slide before also. Let's take a look at the implications of multi-cycle microarchitecture in terms of performance analysis. If you look at single cycle microarchitecture, your cycles per instruction is 1, and clock cycle time is long. As I mentioned, it's not long. It's long, right? You could actually extend it for, I don't know, several seconds. Whereas multi-cycle microarchitecture, cycles per instruction now can be different for each instruction, and clock cycle time is short, right? So you get rid of this long, make it short, but the trade-off is now your cycles per instruction increases. And this is very fundamental also. Whenever you reduce your clock cycle time, your cycles per instruction actually will increase. And we will see that trade-off later on also. So, but the hope is that average cycles per instruction is hopefully small. So the hope is that your clock cycle time will reduce so much that the increase in cycles per instruction is not going to be that bad in terms of performance. So this will be a win on overall execution time. We're assuming the number of instructions is constant. This is purely microarchitectural changes, right? We're not changing the number of instructions. Okay, so that's the trade-off, basically. We're going to reduce the clock cycle time significantly, and hopefully average CPI will not go up that much. And as a result, we're going to win in terms of execution time of a program. Does that make sense? And now we've analyzed this new idea, microarchitecture, in terms of principles and metrics, a principled way of actually evaluating a microarchitecture. Okay, and then there's another thing that this enables, as we discussed. Now you have 2 degrees of freedom to optimize independently. You can optimize clock cycle time, you can optimize CPI, you can keep doing this forever. Okay, let's take a look at a closer look to a multi-cycle microarchitecture. But I guess before we do that, we should take a 10-minute break. So let's be back at 15:15, and then we're going to actually build this from the ground up, if you will. But up to you. I mean, either way could work because it's an archive version. Okay, let's continue our exploration of multi-cycle microarchitectures. So now we're going to take a closer look to a multi-cycle microarchitecture. And you've already seen this actually, which is the LC3 microarchitecture we've gone through, but we're going to build this from the ground up for the MIPS design as well. But this is really the work that introduced the LC3 type of design, and then the design we're going to build up. It introduced the concept of micro-coded multi-cycle microarchitectures or microprograms. If time permits at the end, I'm going to talk about this also, because this is really an elegant processor design. You can see the title is actually very interesting, right? The best way to design an automatic calculating machine. Well, this is Morris Wilks, so he can perhaps write that. But we'll challenge that best way at the end of this lecture and at the beginning of the next lecture. Because it's not going to be the best way, let's say. And then if you actually get a title like this, your immediate reaction should be, what does best mean, right? What is the metric? What are the principles we're evaluating this thing against? Okay, so basically we're going to talk about multi-cycle microarchitectures. And the key idea for realization is what we've already seen. One can implement this process instruction step as a finite state machine that sequences between states and eventually returns back to the fetch instruction state. Basically, you can design a finite state machine that implements every single instruction, and that can be realized using data path and control logic. And we view the processing as sequencing between those states to execute every single instruction. And what is a state in this particular case? Basically, the state is really determined by the control signals asserted in it. Of course, you design the finite state machine, but while you're sequencing through the finite state machine states, you determine the control signals. What should the state do? What should the machine or the microarchitecture be doing in this particular state? So we generate control signals, just like we did in the single cycle microarchitecture, but in a slightly different way here, so that we can actually do what is specified in that particular state. Remember, in the single cycle microarchitecture, we generated the control signals so that the entire machine does everything that's needed to process an instruction, right? Because you go through one state only to process the instruction. Whereas in finite state machine that's designed for multi-cycle microarchitecture, we're going to generate the control signals that are needed to perform what is specified in that particular state itself. So it's a much more bounded set of control signals. Well, I shouldn't say much more bounded, but basically you're dealing with a smaller part of a machine, potentially, as you're not dealing with the entire instruction. You're just dealing with a single state that's part of an instruction's execution. And you determine the control signals for the next state in the current state as much as possible. So while you're doing data path processing in the state, you're also determining the control signals. What should the control signals be in the next state, meaning next cycle? So you're overlapping data path, data processing, and control processing, if you will. So basically, the state machine should enable every instruction to go through the processing cycles, as we will see. So how do you design this? Basically, we divide instruction processing into states. And the stage in the instruction processing cycle can take multiple states. So fetch stage, for example, can take 3 states, as we have seen earlier, right? We're going to see this again. And a multi-cycle microarchitecture sequences from state to state to process an instruction. And the behavior of the machine is completely determined by the control signals in that state. So those control signals specify what should be done in that state. So this is very important. And we're going to make it even more principled toward the end if we have time, as I mentioned. And the behavior of the entire processor is specified by the full finite state machine. So what do you do in a state or in a clock cycle? So in this particular case, state is the same as a clock cycle, but you can remain in the same state multiple clock cycles, as we will see with memory. So control signals do control two things. One is how the data path should process the data, obviously, right? Because this is the same as what we've done in a single cycle microarchitecture. And you also figure out how to generate control signals for the next clock cycle. And this is actually nice because now you're overlapping control processing and data processing. So let's take a look at the state machine that we did. Essentially, the state machine obeys the principle that I just mentioned over here for a basic multi-cycle microarchitecture. So you can see that you have 3 states to do fetch, 3 clock cycles in other words. And basically, each state specifies what should be done in the data path and also control signal generation. But it's not shown in the particular state over here. But basically, you need to set the control signals such that PC program counter from its register gets placed into the memory address register. And also a PC gets incremented at the end of the clock cycle, right? So at the end of the clock cycle, MAR should have the value PC, value that was in PC, and PC should have the incremented value of the PC. Okay, that's the specification of the state. So you need to basically select the control signals, you set the control signals appropriately to do that. And we've done this. You remember that we've done this, not the previous lecture, but when we actually introduced the instructions in LC3. Now we're going to build this machine from scratch for MIPS in a little bit. But basically, this is the finite state machine controlling a multi-cycle LC3 microarchitecture. And each state has to specify the control signals to make sure whatever is specified in the state is done. Of course, somebody designs this finite state machine. Microarchitect says, okay, I'm going to process the instructions this way. So I'm going to divide the instruction processing into small chunks such that I get a high clock frequency, and each chunk will be executed in a state. And now I'm going to provide the data path elements to actually execute what is specified by each chunk, meaning each state, and design the control logic to enable the execution of each chunk, each state, as well as the transition or sequencing between states. And we're going to do that in a little bit. Here again, somebody designed this for you, and this is a full finite state machine controlling a multi-cycle LC3B microarchitecture. You could actually design this, you could actually develop a state machine like this for any instruction set architecture, except it won't be this simple, right? If you want to develop this for x86, if you're designing a multi-cycle microarchitecture, it will have a lot of states, if you will, because there are lots of instructions, lots of things to think about. And remember, there's a decode state where there's a multi-way jump in the finite state machine over here. Okay, we've gone through this before. And remember, this finite state machine always goes with a data path. So when you're designing this, you should design the data path, you should design the control logic, control signals, and you should design the finite state machine. Usually you start with designing the data path, like we did with single cycle microarchitecture, and we will do that again today, not for this one, but for something else. But you can also design things relatively concurrently as well. Now, if you have a machine like this, you can also start adding states. For example, you don't have an instruction, you want to add an instruction. That's easy. You basically add another state over here after decode and specify the states that this instruction should go through. So you need to modify the finite state machine when you want to add an instruction. You need to provide the data path elements to process that instruction if they don't already exist. If they do already exist, that's good. You just need to specify the control signals to make sure the instruction gets processed through the states that you designed. And you need to add the control signals to process the instruction appropriately if they don't already exist. So if you want to add an instruction that does multiple adds, probably all of these signals already exist. So these states actually can be done without changing the data path or the control logic. You just change the sequencing, how you do the sequencing in the machine. We'll get back to that. Any questions? So now let's build, if there are no questions, let's now build the microarchitecture as opposed to taking it as a given. So this was the single cycle microarchitecture in your readings. If you've done the readings, you're very familiar with it. If you haven't done it, don't worry, because it's very similar to what you have seen, what we have built in the last lecture. Now let's make it multi-cycle. And let's take a look at this thing over here. So if you look at this single cycle microarchitecture, apart from all of the other downsides that we discussed, it also has 2 memories and then 3 adders, as you can see over here. maybe that's not efficient enough. Right? So basically, we already discussed that single-cycle microarchitecture has low clock frequency, and it has 3 adders or ALUs and 2 memories. So you have high hardware cost. So with a multi-cycle microarchitecture, we want to achieve higher clock frequency, as we discussed. And we want to enable simpler instructions to take only a few clock cycles and reuse expensive hardware across multiple cycles. Expensive hardware meaning memory and ALUs in this particular case. Right? But of course, this will come at a cost, which is hardware overhead for storing intermediate results and sequential logic overhead to latch the results in the registers, into intermediate registers. Right? So we will basically design this multi-cycle architecture. We're going to design the data path and the control logic very similarly to we would design a single-cycle microarchitecture, except we're going to make it multi-cycle. So what are we going to optimize? Basically, remember that single-cycle microarchitecture uses 2 memories, instruction and then data. Or we could have used multi-ported memories. One of you asked the question. Nice, it was a good question, basically. You could use multi-ported memories, but 2 memories are easier to visualize, if you will. But one memory stored the instructions, the other data, but we want to use a single memory. So let's have lower cost, if you will. Single-cycle microarchitecture needed 3 adders. One is the ALU, one is the program counter increment adder, and the other one was for the branch address calculation, if you remember. We want to use only 1 adder, or 1 ALU, let's say, for everything. This is lower cost, right? You don't replicate the adders unnecessarily. And we already discussed this. Single-cycle microarchitecture had this each instruction taking 1 cycle, but we want to determine the clock cycle time independently of instruction processing time. And I already harped on it, so I'm not going to talk more about it. So let's construct the multi-cycle data path that are going to essentially enable these optimizations compared to the single-cycle data path. So I'm going to start with the load word instruction in this particular case, because it's going to actually exercise a lot of the data path. If you remember, load word was the longest taking instruction for the single cycle, and load word actually exercises all of the stages. That's why it's good to look at load word. And again, don't worry about the exact register names over here, but load word calculates the address, a base register plus offset, accesses memory, and writes the result into this destination register. So basically, you need to fetch the instruction, fetch the base register, do the address calculation, base plus offset, and then read the memory using that address and write to the destination register. So you need, basically, we're going to do the same thing we did for single cycle, except we're going to do things step by step, meaning we're not going to require 1 clock cycle to do everything. We're going to add registers, intermediate registers. For example, I decided to divide the execution of this instruction, processing of this instruction. The first step will be fetching the instruction. So you need to have these data path elements, program counter, and you input the program counter as the address to the instruction / data memory in this particular case. So it's a unified memory. And then it takes some time to fetch the instruction, and then I'm going to latch the results. I'm going to add a register over here saying this is my instruction register. And that's going to be 1 cycle, hopefully. Makes sense, right? Okay, so for this to work, I need to have a control signal that's added to control this one. And that's enough for now, basically. So that's going to be the purpose of the fetch state, and all instructions will actually go through this fetch state in the same way. Okay, so what's going to happen next in load word? We take some bits from the instruction, bits 25 through 21, use that as the address into the register file, and we're going to read the register, and I'm going to latch the result at the end of the clock cycle in a D flip-flop, for example, if you remember from the sequential logic lectures. So that's going to be another clock cycle to do that. So I read my base register. That sounds good, right? Okay. And concurrently, I'm going to sign extend the stuff that's inside the instruction register, right? That's going to be our offset or immediate sign extended, okay? And we've seen this also before. And then we're going to supply that to the source register, the second source of the ALU, and also the data that was latched in the prior cycle to the first source of the ALU. And this is going to be my address computation logic. And I'm going to set the ALU control appropriately such that the ALU does an add operation in that particular state in the finite state machine. Now, this is one state in the finite state machine, fetch. This is the second state in the finite state machine, read registers / decode, let's say. This is another state in the finite state machine, calculate address for this particular instruction, right? Makes sense, right? Okay. And then I'm going to store the result of the ALU into this intermediate register that I'm adding. Let's call it the ALU result register, right? And I don't have a particular write enable value because of the way I'm designing this right now. Later, I may actually change it. I don't want to keep writing to these registers, but I could also keep writing to these registers every clock cycle, right? Depends on what I'm going to do. Okay, now I'm going to take, now this is the address, right? Based on the specification of the instruction, this is base register plus sign extended offset. ALU provides the addition of that, and I've latched it. In the next clock cycle, I'm going to take that address, feed it to my single memory. To be able to do that, I need a multiplexer because multiplexer, we used this memory to take the address from the program counter in the fetch state of the finite state machine. When we are in this state of the finite state machine, we should use this address coming out of this ALU out register. So I need a control signal, whether the memory should be addressed with an instruction or some data address. And I need to set that control signal appropriately so that I can get the data, correct data from the correct address as specified by the instruction and latch it into another register over here. Make sense? So in that state, now I access the same memory with a different address, and I add the data path element to access the memory and set the control signal appropriately. And I don't want to write the data that I read into the instruction register because I want to keep it around, let's say, because I'm going to do something with it later on. And it doesn't make sense to write it over there, but you could potentially reuse that if you design a different sort of finite state machine. So I add another register to latch the data that's coming out of the memory. And that's one clock cycle. So the beauty here is, as you can see, we can use a single memory to both fetch an instruction and fetch an operand, except we're doing it in different clock cycles. Okay, we're not done yet. The next step is writing that data value that we fetched from the memory into the register file as specified by bits 20 through 16 of the instruction. That's why we did not want to clobber this. That's why I needed another register over here, because I'm going to use those bits 20 through 16 in the instruction to figure out what my destination register ID is. And I should set the reg write signal. So the control signals are actually very, very similar to the single cycle microarchitecture. We had a reg write control signal. We had an ALU control signal. But we also need to add some other control signals like instruction register write, because we did not have an instruction register before. We need it if you want to do things in multiple cycles. And also this multiplexer is different because we had two different memories before, right? And that's it. We're done with, well, we're not done because what we've done is every instruction also increments the PC, so we're going to do that. But we're done with the non-PC, non-control flow part of the load word. And this is the data path. These are the control signals. And this is done in multiple clock cycles, as you can see. But we also need to not forget incrementing the PC. As I said, here we don't want to add another adder. We want to use the same adder in the ALU. So what we're going to do is add a path from the program counter into the ALU. So we could the first source input of the ALU can take either the program counter or the base register that we had used in an earlier clock cycle, let's say. So you need a multiplexer also to select between them. And we want to increment the PC by 4. So you need a 4 input and another mux over here, which we're going to populate later on, to actually select between 4 or sign extend immediate, or it's going to come from a register or somewhere else, as we will see. So we're going to complicate the front end of the ALU, if you will, because we want to actually increment the PC using the adder in the ALU. Makes sense, right? So instead of adding another adder, we're using this adder. We could not do this in a single cycle microarchitecture because ALU would be doing address calculation, and you cannot clobber the address. So you cannot do two things in the ALU. You need to have two different ALUs. Now, because we're doing things in different clock cycles, in an earlier clock cycle, we use the ALU to do the address calculation. We've gone through that. Now, in this clock cycle, I'm going to use the ALU to increment the program counter. And I just provided the data path elements plus control signals, controlling this mux, and controlling the writing of the PC program counter. Makes sense, right? So now this is beautiful. We do not have two memories, and we do not need two adders for a load word. And that's the load word. Load word is done. Now let's add to this data path. Is everybody okay with this? Happy with load word? If you can do load word, the rest is relatively easy. Loads are usually the most complicated things in a machine. That's true we're going to see that later on, actually, in a couple of weeks after Easter. Those are going to complicate our life a lot more. Okay. So if you're not fully understood it, you can go through it. And you can also, this is directly from your book. Your book also explains it this way, and you can find it. So let's take a look at store word. As I said, store word and load word are very similar, except store word writes to memory and also doesn't write to a register. So to be able to execute the store word, you need to read the base register. So you have some data, just like load word, and then calculate the address in an earlier cycle. But you also need to read the data value or the register that you're going to write to that address. So these are specified by bits 20 through 16 of the instruction. And the data comes out of the second read port of the register file. And we have an extended register, which stores two data values coming out of the register file. So if you look at load word, we have this register, we read one of them. But for store word, you need to read basically both of the registers, which makes sense. And then you need to have the data path wires to connect whatever you read, and you latch it. So this happens in one clock cycle. And in some other clock cycle, you basically write that value to the location that's specified by the adder. And we already have that path. It's the same as load word, basically. That path is from here. So you just need to make sure that this data value gets written to that address, and this memory write signal is asserted when this address is available. That makes sense, right? So basically, one clock cycle it takes to make the address available. After that clock cycle, the next clock cycle, you take that address, feed it here, set the memory write signal, and the data value flows through this register into the write port of the memory, or write data port of the memory. Basically, we've provided the data path elements. We just need to set the control signals appropriately in a given cycle. And we're going to see that also. Okay, so what about R-type instructions? Now, this was store word. R-type instructions also read two register values, but they basically operate on two register values in the ALU. So we need to provide the data path for that. So this is nice, I guess. And then we need to provide some more. Yeah. So basically, we need to operate on this value, which was provided already. We need to add a little bit more data path wires such that we connect this register to this port of the ALU and then set the ALU source appropriately, of course, which is not shown here. And then we also need to handle this mess over here. If you remember, we had this in the single cycle architecture also, because the destination register of an R-type instruction is specified by bits 15 through 11, whereas the destination register for load was specified by bits 20 through 16, right? That's what this multiplexer is. And this is the same multiplexer that you had in the single cycle microarchitecture, if you remember. So you need to set the control signal appropriately based on the instruction. This is what this means. And you need to take the data value coming from the ALU output in the appropriate cycle and write it into the register file. So remember earlier, we had the data path for the store, for the loads where you can write the data value from memory, and after latching it in the previous clock cycle to the destination register. Now we have this path from latched value after the ALU result coming into the register file also. So you need another multiplexer, and you need to control that multiplexer. This is actually also very similar to what we have seen in the past. There was another multiplexer, if you remember, in the single cycle microarchitecture. So the data path has actually a lot of similarities to single cycle microarchitecture in the end, except we do things over multiple clock cycles. So we need additional registers, but we can be also frugal. We got rid of one memory. We got rid of two adders. Okay, so let's also do the branch equal. Basically, branch equal needs a little bit more work. I'm just adding the things that are needed additionally into the data path. So you basically need to calculate the target address as, so, okay, we don't want another adder to do this. We're going to calculate the target address using the ALU again. So we're going to take the PC. So there was already a path to increment the PC. Instead of incrementing the PC, we're going to add to PC the sign extended 16-bit immediate left shifted over here. So now you can do target address calculation as program counter plus that. Makes sense, right? So basically, you provide the data path elements to make sure that this target address calculation can be executed in the ALU without having another adder. And then, of course, you need to have this branch condition determining logic. If branch equal means that the subtraction of the source register and destination register is 0. If it's 0 and if it's a branch, then PC write should be enabled. And the PC write should get the results that's latched at the end of the ALU over here. So you need to make sure appropriate control signals are asserted at the appropriate cycles. And that's why we're going to see the finite state machine next. This makes sense, right? So we're basically providing the data path elements incrementally to execute more and more instructions. And we could keep doing this, but I'm not going to do that to execute more instructions. That will keep complicating the data path, but this is the data path for the complete multi-cycle MIPS processor that we have, that is in your book, essentially. Okay. Now, realize that there are extra registers not needed in a single cycle design. We've added 4 of these registers so that we can store the intermediate results. Not good, perhaps. But what we gained was a faster clock cycle. We don't need to do everything in a single clock cycle. And we gained something else. We have only 1 memory as opposed to 2. And we have only 1 ALU or adder as opposed to 3. Yes, we have some bigger muxes here and there. That's true. So there's some other logic that has changed to make sure that we can use only 1 memory and 1 ALU, like this multiplexer over here and this multiplexer over here, and then this multiplexer over here. Does that make sense? Okay. So now let's construct the multi-cycle control logic. Just like we did with single cycle, we construct the data path. Now, how do you construct the control logic? We need to basically have a control unit. It's a finite state machine, as we discussed. This control logic is a finite state machine. It's different from single cycle. But the control signals are mostly similar to the single cycle microarchitecture, except we added some more, of course, like this I or D. This basically determines whether the address of the memory should come from instruction register or the result of the ALU, if you remember. And then this also existed, actually, ALU decoder, because you need to whether it's if it's an ALU operation, then you need to decode the function. And then there needs to be some control logic over here. So basically, let's construct this finite state machine. So every instruction needs to be fetched. This is state 0. And reset state is also state 0. Remember from the finite state machine lectures, you always need to have a reset state. So what does this fetch state do? It takes the program counter, uses it to address memory, and gets the data and latches it into the instruction register. Meaning that this multiplexer should select this I or D signal should be 0. Memory write signal should be 0. Do no harm. Don't forget to do no harm. Basically, if you're not changing anything else in any part of the machine, do no harm. So all of these control signals also should be set to 0, like this one. Actually, some of these do not necessarily need to be set to 0. Actually, I need to go through that later on. But let's do this again over here. Basically, you need to select this PC to flow through this mux. Don't write to memory, read from memory, and ensure that at the end of the clock cycle, data is latched into this instruction register, which means that set IR write to 1. Okay, so IR write is set to 1, and this is set to 0. I or D is set to 0. And we're going to increment the PC in this cycle. That's what the designer decided. So PC needs to also flow through this, as you can see. It's not very well shown over here, but you need to select the source 0 over here. That's why these are set. You need to select source 0, 1 over here. So this control signal, ALU source A needs to be set to 0. ALU source B needs to be set to 0, 1. And then the operation of the ALU control needs to be 0, 1, 0, which is not said here, but it's decoded using ALU op over here. And then you need to make sure that PC is enabled, right? And for that, you need to set PC write to 1 over here, which means that you're going to write to the PC, regardless of the output of this logic over here. This output is used for conditional branches, and branch should be 0 in this particular case because ALU should have no effect. But if you set this to 1, it doesn't matter what this is. Actually, this could be X, if you will, right? So you could actually change some of these to X. But this is the control signal. You should set the control signal such that fetch the operations that are specified by the fetch stage, which is fetching the instruction and writing the instruction to the instruction register, and also incrementing the PC is done. Very similar to how we did it with the LC3B in a different kind of hardware. Okay, and then the next state, sequencing, is unconditionally the decode state. So what happens in the decode state? We examine what's in the instruction register. Right? So basically, there's some magic that happens in the control over here. But we're not, decode state actually, in this particular state, you actually get the values that's flowing through the instruction register. You read the register file. So unconditionally, you read the register file. So some of these signals are set accordingly. Okay, let's take a look at what happens if the opcode is load word or store word. The next state in the finite state machine is load word or store word. This is the memory address computation state. Basically, you take the values that were latched here into this register in the decode state, and you need to make sure that you calculate the address. So this multiplexer should select the bottom data input, and this multiplexer should select the sign extend immediate coming out of the instruction register. And the result should be latched over here. So you set the control signals accordingly. Basically, I just said all of these basically. ALU source should be 1, ALU source B should be this one, sign extend immediate, and ALU operation should be an add, which is 0, 0, which is the same as PC plus 4, right? That's an add. Okay, so that's, and then the rest is do no harm, of course. Of course, you're not writing to memory, and you're not writing to the register file. So do no harm. Some of the other signals can be X's, meaning don't cares, because they're not going to do any harm anyway because of the write enable signals being set to 0. Okay, so that's the memory address calculation stage. And then there's the memory read state. I could keep going through this, but I'll let you do some of these things. But basically, if the operation is a load word, in the finite state machine, you go through another state over here. And then you set I or D to 1, meaning the address is coming from over here, ALU output, so that you can actually read the data from memory. And then you transition to another state where you write to the destination register the appropriate value. So this is the execution of load word. Fetch, decode, calculate the memory address, read the memory, write back the result that you read from memory into the destination register. And in each stage, you need to set the appropriate control signals, and each state takes 1 clock cycle. Makes sense, right? So we could keep going through this, but this is one way of designing the finite state machine. Here, you basically take another branch. If the operation is a store word, you do go to a mem-write state after you calculate the memory address state calculation. After you calculate the memory address, because the calculation of the memory address is the same for load word and store word, if you remember. So you need to set the appropriate control signals, as you can see over here. Okay, so this is R-type instructions. After decode, you need to go through R-type, and I'll let you go over it. But we've kind of done it when single cycle, multi-cycle is very similar, except you do things over multiple cycles. And then branch equal requires another state. And also branch equals tasks are distributed, actually. You can read your book, or you can read these signals over here. Some of the tasks are done over here. This is the target address computation. And this is actually the branch determination. Why? Because we're using the same ALU to compute the target address, as well as to compute whether we should branch, subtract 2 registers, right? So target address computation is done here by setting the control signals like this, and computing the subtraction, whether 2 values are equal, is done here by setting the appropriate signals. Does that make sense? Okay, so it's all about controlling what the data path is doing using the right control signals. And this is the complete controller finite state machine for the data path we designed for the set of instructions that cover these instructions, which looks very simple, right? Even simpler than LC3, because LC3 has more instructions in this particular case. And now you can actually extend by adding add I, right? If you want to do add immediate, you can add more states to the finite state machine, and you can add more control signals and data path elements as needed. It turns out for add I, data path elements are not needed, but you need to set the control signals appropriately. So you can add a new instruction, assuming that you constructed a finite state machine and data path that looks like this. Add I comes for kind of free, because you just need to extend your finite state machine, decode, go to another state over here, and then there's an execute state, and then there's a write back state that you add for add immediate. It so happens that the data path elements and control signals are already there. You just need to manipulate them in the right way and set them in the right state so that you enable add-I functionality. Makes sense, right? Okay, so if you want to extend functionality, so sometimes if you want to add another instruction, you don't have the data path element, so you need to extend the functionality. For example, adding jump, we've done that also in the single cycle data path. You need basically to extend this multiplexer over here because jump calculates the address in a different way. It takes the bottom 26 bits of the instruction, left shift it and concatenates it with the incremented program counter, which is supposed to be somewhere over there. Yeah, well, you can figure it out. Program counter was incremented in an earlier state, if you will, which is the fetch state. So jump requires some more additions to the data path and one more control signal or extended control signal for this multiplexer and another state in the finite state machine. So basically, this is how you could keep adding instructions to execute in a machine. And it's beautiful. Okay, so you just basically the takeaway is you need to add the state. You need to ensure that data path elements are there and they can execute the instruction. And you need to orchestrate the flow of data as specified by the state that you've added by setting the control signals appropriately as specified by the state. So now we've constructed a multi-cycle MIPS microarchitecture. And that's it, basically, assuming that's your whole instruction set. That's it, of course. So remember that this was our single cycle MIPS microarchitecture. It looked like this. This is the state machine. And this is our multi-cycle MIPS microarchitecture. It kind of looks similar, actually, except we added some things, we removed some things. But control signals are fundamentally, let's say, relatively similar. And the difference, the major difference is you have a finite state machine orchestrating the execution of an instruction and the sequencing. Well, it's always good to ask, what is the shortcoming of this design? I'm looking for a particular shortcoming, but since we don't have time, I will not let you think about it. Basically, this design assumes something about memory. Every state takes one cycle, right? But we said that sometimes memory can take a lot of cycles. So what do? Well, easy. You have this finite state machine, change the sequencing such that you stay in the memory access state until memory returns the data. So memory can tell you whether it returned the data. Basically, memory ready bit. This could be a bit supplied by the memory. You supply the address and basically enable the memory, and that memory at some point says, oh, I set the memory ready bit, which means that my output is ready. You take this and use this as an input into the control logic that determines the next state. So let's take a look at this. We've actually seen this. So this is from LC3B. If the memory takes longer, you check the ready bit. So if you're in this state, and if the memory is ready, go to the next state. Good, take the data value from the memory data register and put it into the instruction register. If you're in this state, but if the memory is not ready, well, stay until memory is ready. If the memory takes 1 billion cycles, well, I'm going to stay in that state, twiddling my thumbs 1 billion cycles. But I'm not going to change my clock cycle. My clock cycle is still 10 gigahertz. Makes sense, right? This thing does not affect my clock cycle. I can execute my ads fast. Of course, 1 billion clock cycles is not good. And we're going to see that. That's why the last third of this class is dedicated to memory. How do we deal with memory? These are the bottlenecks in a real system, this memory access. Okay, well, they exist in loads and stores, as you can see. These are memory access states, and you wait until memory is ready. You don't need to assume it's 1 cycle, 2 cycle, 5 cycles. I don't care. Whenever the memory returns the data, I'm going to go to the next state after that point. Okay? So that's the beauty of this design. This design doesn't have the huge shortcoming that we have discussed earlier. It enables us to deal with memory in a much nicer way as well. Any questions? Okay. You'll understand this better when we talk about memory. But let me foreshadow memory by saying that these are the bottlenecks in today's systems, because memory takes long. You can see that the addition is 1 cycle, right? You don't wait until the addition. You could also do that. If any state needs more time, if the adder, multiplier, square root, divider, whatever you have in the instruction set takes longer, you can stay in that state for some time. Okay, so let me give you the basic principles of another architecture, because this is also very clean. And this is what prompted Maurice Wilks to call his machine the best way. let's talk about it. Because this will enable some other opportunities that exist in all of the machines today. So hopefully we'll finish it in time. But basically, you can formalize this, and people have formalized this. So control signals associated with the current state can be viewed as a micro instruction. So we have instruction in the ISA. Control signals specify what the machine should do every cycle. You could think of it as a micro instruction. It controls everything in the machine. Now it's beautiful, right? This is an instruction that's not visible to the programmer. It's an instruction that's visible to the microarchitect. That's why it's called a micro instruction. So now you can think about sequencing from state to state as applying micro instructions into the machine, which means that you have a micro program running on the machine. So basically, act of transitioning from one state to another means determining the next state and the micro instruction for the next state. That's called micro sequencing. So you have a control store that stores control signals for every possible state in the machine, meaning that you can store the micro instructions for the entire finite state machine, analogously how you store a program in memory. Now, very interesting. And the micro sequencer determines which set of control signals will be used in the next clock cycle, meaning which micro instruction you will execute. Now, this is not an instruction you execute. These are the control signals that you apply to the hardware. But I said you execute a micro instruction because it's very similar to how you execute an instruction, except it's a much lower level of abstraction at the hardware. This is directly controlling the hardware. Okay, so this is the control structure basically that I'm talking about. You have a control store memory. This, you have 2 to the 6 possible states, 64. Each micro instruction is 35 bits. So at the beginning of a clock cycle, you fetch your micro instruction. These are basically all of the control signals that are needed to execute, enable the processing that happens in the data path in that particular state. And also you use some of them as well as some signals coming from memory, for example, and the opcode to determine what should your next state be? What should your next micro instruction be? So every cycle you do this. You do processing and you decide what should your next micro instruction be, meaning next set of control signals in the next state. This is a program basically at a much lower level, not visible to you. So that's what this is about. I'm going to give you some further study and also some lectures, but I'm going to mention this a little bit more right now. So basically, control signals are the micro instruction. You apply that micro instruction to the data path as well as the control logic concurrently in the same clock cycle to determine what the data path should do and what should your next state be. So you fetch the next state, next micro instruction. So I think I already said this. The control signals are micro instruction for the current states, control the processing in the data path, and they generate the control signals or the micro instruction for the next cycle. And the data path and micro sequencer operate concurrently. Well, basically, we generate control signals for the next cycle, not the current cycle, because we don't want to serialize the processing. And your book has a beautiful description of it. But let me give you a little bit more over here. So now we have 3 components. It's actually very beautiful. You can design these in a very nice way. You have micro instruction, control signals that control the data path and help determine the next micro instruction. Each micro instruction is stored in a unique location at control store. It's just a special memory structure. And each state in the FSM corresponds to one micro instruction. And microsequencer determines the address of the next micro instruction. So this is programming. So we can call this a micro program. The control store has the micro program, which is really how you would sequence through states in the finite state machine. This is a control store, 64 entries. Each entry in the control store is a micro instruction corresponding to a given finite state machine state. And FSM state number is used to address the control store to get the relevant micro instruction. So, okay, basically a simple, so you can actually do the micro programming. I'm not going to ask you to do it, but if you're interested, you could write this micro program, 1s and 0s, to execute a load word instruction sequentially as specified by the finite state machine. You need to know what's going on in the data path, of course, right? And also the micro sequencer. I'm not going to ask you to do this, but I will mention something that's really important and that will tie us to the ISA. Basically, this concept of a control store of micro instructions enables the hardware designer with a new abstraction. The abstraction is micro programming. And the designer now can translate any desired operation to a sequence of micro instructions, control signals that are executed at a given state, and then you sequence through them. All the designer needs to provide is the sequence of micro instructions needed to implement the operation, the ability for the control logic to correctly sequence through the micro instructions, and any additional data path elements and control signals. But you don't need these if the operation can be translated into existing control signals. So if you have the existing hardware, you just do micro programming. which is beautiful. So let's take a look at this picture that I showed you earlier. You have the high-level language at the top, hardware control signals. We said that, okay, ISA is here. There's a small semantic gap for a complex ISA. But you could have an implementation ISA with simple instruction and data types and addressing modes. We said that you could have a software or hardware translator between them. And we said that, for example, Apple in its M1 translates x64 to ARM v84 so that they can fix the trade-offs over here. Now, what we're looking at with the architecture that I showed you as microprogram microarchitecture is we have a hardware translator, which is a micro sequencer. This is it could be any ISA, and these are micro instructions. So every machine does this basically. It depends on the complexity of your micro instructions, and existing machines do it in a very, very interesting way. So let me finish this and then we're going to be done. But basically, there's actually very, very interesting things that can be enabled with this. This allows a very simple design to do powerful computation just by controlling the data path using a sequencer. I think we already said this. You basically translate the high-level ISA to a sequence of micro instructions, and microcode enables a minimal data path to emulate an ISA. And micro instructions can be thought of as a user-invisible ISA. It also enables easy extensibility of the ISA. You can support a new instruction by changing the microcode. This is also called microcode. You can support complex instructions as a sequence of simple micro instructions. You just need to modify your finite state machine. For example, you could do multi-dimensional array updates or string copies by sequencing through micro instructions. And very interestingly, this also enables update of machine behavior. A buggy implementation, for example, that's found in the field can be fixed by changing the microcode. You could have a microcode update that Intel sends to you, and you patch it, and your buggy hardware becomes not buggy anymore. Right? Okay, so this is where I'll stop. You can read this slide because that's the last slide. But if you're really interested in this, there's a lot of interesting things over here. And we're done. Tomorrow we'll start with pipelining.